Okay, we are back again. Next is torque developed in a motor. So, this is also that your what you call this motion is given, this commutator segment, these are brushes and these are the conductor placed, right. Here it is, look at that, here it is make plus and this is N pole and here it is S, right, here it is dot. So, this means current entering into that and leaving the page. I mean this is your convention, right, and this is the production of torque and this is your what you call it is a it is cylindrical in shape, right. So, you will find things are simple, that now when the field of a machine is excited and a potential difference is impressed upon the machine terminals, the current in the armature winding reacts with the air gap flux to produce a torque which tends to cause the armature to revolve, right. This is actually figure 3, this is actually figure 3 and these two dots are here, this is basically the neutral zone, right. So, figure 13 illustrates the production of torque in a motor. Now, when the brushes are on the neutral axis, all the armature conductors lying under the north pole carrying currents in a given direction, while those lying under south pole carrying currents in the reverse direction, right. So, if you look into this, this is your neutral zone. So, all the currents in under all the conductors under the north pole flowing in one direction, right, and in the south conductors under south pole carrying current in the other direction, because one going into the page, another is you have to call leaving the page and this is the brushes, right. So, the commutator serves to reverse the current in each armature coil at the instant it passes through the neutral axis. So, that above relation is always maintained as the armature rotates. So, when armature will rotate the commutator segment, this polarity this will maintain, right. Whenever it is at any instant when it is passing this neutral axis. So, this polarity of these two your two brushes always will remain same, right. So, that is your you have in a DC machine you have several your brushes, your what you call several commutator segment if you see that open DC machine. So, in that case that you have what you call, just I told it passes to the neutral axis. So, that the above relation is always maintained as the armature rotates, right. So, commutator serves to reverse the current, right, in each armature coil. So, next is all the conductors under the north pole carry inward flowing currents, that I showed the plus convention, which react with their air gap flux to produce downward acting force and a counterclockwise torque. So, this is your what you call, this is the diagram, because this all the your force diagram are given diagram from stronger magnetic field to the weaker one, everywhere from this diagram it is, look at that, arrow is downward, here it is upwards, right. From that you can find out that torque will be developed, right. So, in this case under the and it produces downward acting forces and a counterclockwise torque, right. Similarly, the conductors under the south pole carrying your outward flowing current which produce upward acting force, these forces also give rise to the counterclockwise torque. So, in that means if the air gap flux is assumed to be your what you call radially directed to all points, right. So, each of the force act tangentially and produces a your what you call turning moment equal to the force multiplied by its lever arm, right. Therefore, that is the radial distance from the center of the conductor to the center of the shaft. So, this way we know the force equation, we know the EMF equation, right, everything we know. Therefore, the magnitude of the torque developed by each conductor will be BIL, this is the force into R in Newton meter, right. Where R actually your what you call this R actually measured from this, actually it is a cylindrical shape, right, it is a cylindrical shape not shown in this diagram, it is made from center to this to that part, right. So, it is a radius. So, all this write up is there, just read carefully. So, this is my torque equation BIL into R Newton meter. Now, if the motor contains Z contactors, the total torque developed by the armature will be BIL R into Z Newton meter, because that was for one conductor, but total will be BIL R into Z Newton meter. Now, B is equal to flux density Weber per meter square, I armature current in a conductor, that is ampere, L is equal to length of each conductor, that is meter, and R is average radius at which conductors are placed, that is also meter, and Z total number of armature conductors, right. Now, if IA is the armature current, then for your I should be equal to IA upon A, that means your what you call IA is the armature current, then and you have a number of parallel path, right. So, I should be is equal to I a upon a, right. So, second thing is the flux density B should be equal to phi upon small a, right, and your A is the number of parallel paths, right. So, it is uniformly distributed. So, it is you are uniformly distributed. So, it will be what you call the current per your what you call per path, and this is phi upon a Weber per meter square. Phi is the flux and A is the your cross sectional area. I mean, what is this? We will see that. Now, A is equal to cross sectional flux path at radius r. That means, you have to find it is 2 that is it is a cylinder, its surface area is 2 pi r l, if L is the length, r is the radius, and flux path at radius r, that means basically it is basically 2 pi r l by p, that is surface area per pole, right. So, that is why cross sectional flux we call it is a flux path at radius r, it will be 2 pi r l upon p. 2 pi r l is that your we are assuming it is a cylindrical, so surface area, right. Therefore, if you substitute all, you will get T is equal to Z phi L into I r upon 2 pi r l into p by a Newton meter. That is, or we can write same equation T is equal to Z phi I a upon 2 pi into p by a Newton meter, or your 0.159 then Z phi p I a upon a 7, then 1 upon 2 pi you make it, right, it is 0.159, or T is equal to then this is a constant, this is a constant. So, T all these things are constant. So, we can write your T is equal to k into phi into I, that is phi into I a, rate 0.159 Z p upon a is a constant, Z p upon your I mean I have taken this one, right, Z p upon 2 pi a, it is a constant. So, torque is proportional to your what you call proportional to product of flux and your armature current, right, and in that DC machine flux actually depend on the field current. So, flux is proportional to the field current, right. We will see the series motor, shunt motor, how is it. So, that means your another thing before although it is not marked here, but I am telling that flux actually proportional to the field current, right. That means, your torque actually proportional to then your field current, product of field current and armature current, right. Instead of phi we have made it is If. So, the equivalent circuit of DC motor. Now, this diagram I have drawn, this is a separately excited your DC machine, right, DC motor. So, if you look into that, a separately excited means the field actually is given a different your supply, right. I mean from a different source where that DC supply separately is given to your field, and this is your what you call, this is your motor, this is the supply voltage, this is the armature resistance R a which is very small, EB is the back EMF, polarity is marked, and here I a is equal to I L, armature current is equal to load current, R is equal to 0 at running condition. Actually, when you start the DC machine, right, first year also perhaps you will do lab, electrical lab also for this thing or whatever it is, right. Whenever you start the DC machine at the beginning, that R should be at the your what you call maximum position, right, because as soon as you, otherwise as soon as you switch on, back EMF will not be there, and if you make it at a very small your what you call very I mean it is at a minimum value, then armature resistance of DC motor is very small. Therefore, a huge current will flow and fuse will blow if you do not connect fuse somewhere here, right. So, at the time of start what you do, that this resistance should be at maximum, and then you start that what you call that your then you give the supply, then your what you call motor will what you call, so it will start slowly and slowly will pick up, and then back EMF will be developed. Now, after that when the speed is pick up slowly and slowly, you cut the resistance and bring this resistance to 0. But look into that in laboratory what we do, that we have connected one SPST single pole single throw switch, and this switch is open at the when machine when you start and this resistance is maximum, this switch is open. When you cut this resistance to 0, right, maybe because of some contact some little resistance may be there, after that you close this switch such that the path will be like this. So, this is totally off from this, and as soon as you close it, that will give you the what you call that no circuit resistance, no external resistance in this circuit. So, as soon as you just close it, so little bit you will find as soon as you close it, you will find the speed is slightly increased, because here because of the contact or something, some your what you call some resistance was there. That is why you use SPST, a single pole single throw switch, such that you can close it when that means what, that means you start this when keep R is maximum, right, and then when and give the supply. And regarding starter, we will not study in this course, DC machine starter we will not study, but as soon as speed will pick up, slowly and slowly you cut down the resistance, and being the resistance R is equal to 0. Once R is 0, right, at running condition, then you close this SPST switch such that this will be completely cut off and this will be the path, right. So, this is your separately excited, your what you call DC motor, and V is the terminal voltage and your EB is the back EMF. So, in this case, and this is RF, RF is the field resistance, this is the field, this also you can vary, this is your field resistance RF dash, and this is your field, and field resistance is RF, and this is the additional resistance inserted here, this is called RF dash, right, and this is your field winding and field resistance is RF, and this is the supply, right. So, RA is very small for DC machine. I put a question to you, although you are in this thing, how can you measure that armature resistance of a DC machine in the laboratory? This is a question to you, you think, right. So, IA is equal to armature current is equal to load current, and EB is equal to V minus IA into R plus RA. Of course, running condition R is equal to 0. That if you apply here your what you call KVL in this circuit, then you will get, you can easily make it, polarity everything is marked, you can make it, you will get EB is equal to V minus IA into R plus RA, but a running condition your R is equal to 0, right. Now, if it is your, and this is your what you call your shunt motor. So, in this case the shunt field is here, this is a field winding and this is the RF dash, right, this is the RF dash. So, here SPST I have not shown, but you can put it here also, I mean here also you can put it, but not shown here, I did not show it here, right, I did not show it here, you can put it, right. So, I am now cleaning it. So, in this case also philosophy will remain same, only here from the same supply you are what you call, you are giving that you are giving the supply to the machine as well as to the shunt field, because it is your parallel connected. So, this is field resistance, shunt field, it is RF, and this is your RF dash, some external resistance is there, RF dash, right, because by inserting RF dash, right, this resistance you can vary, hence you can control the field current, this IF, hence field current controlling means you are controlling the flux, right. So, but anyway R is equal to 0 at running condition. So, therefore, IF is equal to V upon RF plus RF dash, because this is the current IF, voltage is V, this is a parallel circuit. So, IF will be equal to V upon RF plus RF dash, right. And if you apply your same way, if you apply your KVL, so you will get it, your EB is equal to V minus IA into R plus RA, but at running condition R is equal to 0. And if you apply KCL here, if you apply this is your armature current, this is your line current, and this is your what you call that field current. So, if you apply at this, look at that cursor, at this point you apply KCL, right, you apply KCL at this point, you will get your IA is equal to IL minus IF, right. So, this is a simple thing. So, for series motor actually, series winding actually it is in series with that armature. So, in that case armature current is equal to load current is equal to field current for series motor. Here series field is in series with the armature, it is in series, right, and this is your back EMF and this is V. So, this is series motor. In the series motor armature current is equal to field current is equal to load current. So, and if you apply your and this is the series field resistance RS, right, and if you apply here also your what you call that KVL. So, you will get EB is equal to V minus IA into RS plus RA. RS is the series field resistance. How to control the flux of series field, this that we will not study in this course, just some basic, right, not beyond that at first year level. So, this is equal to EB is equal to V minus IA into RS plus RA. So, let us take one small example. Suppose a 230 volt shunt motor runs at 800 rpm on no load and takes 5 ampere. Resistance of the armature and field winding are 0.25 ohm and 230 ohm respectively. Calculate the speed of the motor when it is loaded and takes 60 ampere from the mains. This is the problem. So, no load condition as well as you say another loading or what you call another, when it is loaded it is taking 60 ampere, but at no load it is taking 5 ampere, two conditions and other things are given, right. So, we have to find out the speed, right. So, this is the no load condition DC shunt motor circuit diagram. This is IL0, this is your what you call IF, because 230 volt voltage supply voltage is V, RF is given 230 ohm, no external resistance shown here, IA0 your what you call your this is the IA0, RA is given 0.25 ohm and no load speed 800 rpm and this is the back EMF. So, field current IF is equal to 230 upon RF, 230 volt is supplied, 230 is the RF. So, 230 by 230 is 1 ampere. So, IL0 is given 5 ampere, it is given because here it is given your what you call on no load and takes 5 ampere, right. That means it is drawing line 5 ampere current from the line. So, IL0 is equal to 5 ampere. Therefore, IA0 is equal to IL0 minus IF. So, 5 minus 1. So, IA0 is equal to 4 ampere, right. Therefore, this circuit only EB0 is equal to V minus RI0, find out the back EMF. So, EB0 is 230 minus RA is 0.25 into IA0 4. So, EB0 is equal to 229 volt, right. Now, this is on no load condition. Now, when it is loaded, this is the circuit. At that time, it is drawing current of 60 ampere, right, and this is the current say IA1, RA is 0.25 ohm. You have to find out what is the speed, right, and this is 230 ohm. That means, field current your what you call IF 230 upon 231 ampere. So, at no load or full or at this load, field current will remain same, again it is 1 ampere. That means, flux remain constant. Both the cases field current constant means the flux remain constant. Therefore, IA1 will be your IL minus IF. So, 59 ampere 60 minus 1. Therefore, EB1 will be V minus your IA1 into your RA 0.25. So, directly I am writing this, you will get EB1 is equal to 215.25 volt, right. This you will get it. So, this is on loaded condition. This is a circuit, you just try to separate circuit and solve like DC circuit. You can only looking at this all these conditions, right. So, after this what we will do, that we know this EB is equal to phi z n by 60 into P by A is equal to K into phi into N, but IF is constant for both the cases. If IF is constant means the flux is constant, right. Therefore, EB0 by EB1 you can write phi 0 N0 upon phi 1 N1, because this is the condition. From here you can write one equation EB0 is equal to K phi 0 N0, another equation you can write EB1 is equal to K phi 1 N1. So, K will be cancelled because these are constant. So, it is phi 0 N0 upon phi 1 N1, because but field is constant, IF is constant for both the cases, current is 1 ampere, therefore, phi 0 is equal to phi 1. So, if it is phi 0 is equal to phi 1, therefore, EB0 we computed 229, EB1 we computed 215.25 is equal to N0 we know 800 divided by N1 the speed. Therefore, N1 is equal to 752 rpm. This is the answer, right. Now, this is one example, we will take another 3 or 4 later. Now, characteristic of DC motors. Now, first is a torque current characteristic. For DC motors, we know that torque is equal to K into phi into IA, right. Now, in case of a shunt motor, the flux phi is approximately constant and the torque is proportional to IA. That is why that previous example I took, because flux for DC shunt motor remain constant, because field supply voltage more or less remain constant, field resistance more or less remain constant. Therefore, flux will remain constant, because field current remain constant means the flux is constant. Therefore, torque actually proportional to IA. That means, it is almost straight line characteristic, right. So, therefore, the curve of torque current character is practically a straight line. Now, in the case of series motor, because series field in series with the armature, so armature current is equal to field current, right. That means, flux is proportional to IA, because torque is equal to your torque is equal to suppose K into phi into IA. For series motor, your flux actually proportional to IA, because in series motor your IA is equal to IF, because series field is connected in series with the armature. So, IA is equal to IF. That means, if phi proportional to IA means the torque actually proportional to IA square. So, that is why this your everything is written here, that is why torque is proportional to IA square. So, if we draw the characteristic, this is the torque, this is IA armature current. For shunt motor it is straight line, right, this is marked it here, and for series motor it is parabola, right. So, this is the torque current your current characteristic of your series motor and shunt motor. Now, second is speed current characteristic. In this case, we know again back EMF is equal to K into phi into N. Actually, N is equal to that example we might have used capital N, but N is equal to small n is equal to capital N. Now, in the case of a shunt motor, we know this back EMF is equal to V minus IRA. right. Under running condition we know that. So, it is E b is equal to V minus I A R A. So, therefore, we can E b is equal to K phi n is equal to V minus I A R A, right. That means, n is equal to, we can write your K dash V minus I A R A by phi, where K dash is equal to 1 upon K, right. Therefore, in a shunt motor the flux phi is more or less practically constant, it is more or less constant, that we have seen also field current more or less constant. So, flux constant, so flux is a constant. Therefore, an IARA drop is very small, because RA actually for a machine is very small, DC machine is very small, right. So, this IARA drop is very small, about 3 to 6% of V. Therefore, the percentage drop is speed from no load to full load is of the same order, right. Therefore, the DC shunt motor is therefore considered as a constant speed motor. Sometimes they ask this question that why DC shunt motor is a constant speed motor, this is the reason, right. So, though its speed drops slightly with the increases in load. So, in the case of a series motor, again n is equal to K dash V minus I A R A, and R S is the series field resistance, here you have to add R S divided by phi. But in the series motor, phi is proportional to I A, because I A nothing but the armature current is equal to field current in series motor, but that is why phi proportional to I A, and series motor I A is equal to I A. Therefore, you can write n is equal to say K double dash V minus I A into R A plus R S I A. So, here actually it is something like this, if it is, if phi, just hold on, if phi actually proportional to I A, that means phi is equal to say some constant K 1 into I A. If you substitute here some K 1 into I A, therefore, K dash upon K 1 we are calling as K double dash, right, something like this. So, if you do so, so it is coming like this, right. Therefore, n is equal to K double dash, this constant V upon I A minus R A plus R S, right. So, this part is constant and it is V upon I A. Here both the phi and I A vary with load, because phi is proportional to I A. If load changes, then armature current will change, and armature current is equal to field current, therefore, flux also will change. Therefore, both phi and I A vary with the load, because phi proportional to I A. If the load increases, phi also your increases with load current, that is I A increases, right. Thus, V by I A decreases, because if I A increases, so V by I A will decrease, right. Therefore, with the increase in load, speed decreases for series motor. So, if the load is removed from the series motor completely, so phi becomes extremely small, right. If you remove the load, that phi will become very small, right, and hence the I A. So, I A also will be decreased, right. Therefore, V by I A is very large and speed is very high, right. Therefore, it is thus dangerous to remove the load completely from the series motor. Therefore, a series motor should always be started on load. So, series motor should not be run on low load. They ask sometimes this question, why series motor should not be run on no load, right, because of this reason only. So, that means series motor, whenever you start, you have to start connecting some load, then you start, right. Otherwise, it is dangerous to remove the load completely for series motor. So, if you, that means for shunt motor, the characteristics are, this is speed current characteristic, this is for shunt motor, and for series motor it is your speed current characteristic, right. Now, another one is the speed torque characteristic. So, in this case also more or less you will find that speed torque characteristic for shunt motor, and here it is speed current characteristic for shunt motor more or less same, right. So, once the, I mean their nature is same, once the speed current and your current torque current characteristics of DC motors are developed, the relation between the speed and the torque in each case can be found out, right. In the case of a shunt motor, speed slightly drops on full load, the motor can be considered as a constant speed motor. This is the speed torque characteristic of DC motor, right. Similarly, in the case of a series motor, nature of the speed torque curve is similar to that of the speed current curve, right. So, these two I did not give here intentionally, I did not give here the mathematics 1 or 2 equations. I suggest this is a small exercise for you, right. The other two I have explained, and this nature of these two and these two are same. Only thing is that you write 1 or 2 equations and just see what whether your what you call same characteristic from your philosophy or what you call, you can get it or not, right. So, next is one example. So, a 230 volt shunt motor with a constant main field drives a load whose torque is proportional to the cube of the speed when running at 600 rpm. Now, it takes 30 ampere. Find the speed at which it will run if 10 ohm resistance is connected in series with its armature. Like actually, you have to find the speed at which it will run if 10 ohm resistance is connected in series with its armature. So, look, this is the circuit diagram, right, and it is given that your what you call that 230 volt shunt motor with a constant main field drives a load whose torque is proportional to the cube of the speed, that means torque is proportional to n cube. When running at 600 rpm, it takes 30 ampere. You have to find the speed at which it will run if 10 ohm resistance is connected in series with its armature. So, this is the circuit first circuit. This is EB1 back EMF. So, drawing 30 ampere, N1 is given 600 rpm and V is equal to 230 volt. So, when N1 is given, IA1 is 30 ampere and let N1 upon N2 is equal to x. N1 is the speed for the first case 600 rpm and in this ratio take N1 by N2 is equal to x, and we know EB is equal to K phi n. Second circuit is that a 10 ohm resistance is connected here, right, and this is in the second case what will be the IA2 and what will be N2, right, and this is 230 volt is given and this is the field current IF. Now, but field is constant. So, in that case phi 1 is equal to phi 2 is equal to phi, and EB1 upon EB2 will be then phi 1 N1 upon phi 2 N2. This should be, this small formula should be on your fingertips all the time, right. So, and therefore, EB1 upon EB2 is equal to N1 upon N2 is equal to x, because we have assumed N1 by N2 is equal to say x, right. So, from figure A, EB1 is equal to 230 volt, that is RA is neglected. So, back EMF 230 volt, from this figure RA is neglected, right. So, in that case your EB1 will be 230 volt. From figure B, EB2 will be 230 minus 10 into IA2, because 10 ohm resistance is added. So, it will be 2 minus your 230 minus 10 into IA2. Divide this, EB1 upon EB2 is equal to 230 upon 230 minus 10 into IA2 is equal to say x, because EB1 upon EB2 is equal to N1 upon N2 is equal to x from equation 2, right. So, that means you cross multiply, and given that the torque is proportional to the cube of the speed, therefore, we can write T1 by 2 to T2 is equal to N1 by N2 whole cube, right, that is x cube. So, T1 by T2 is equal to x cube. So, first condition and this is the second condition. We know that torque is equal to K dash phi into Ia, right. Therefore, we can write T1 upon T2 is equal to phi 1 I1 the first case divided by phi 2 IA2 second case, but flux remain constant for shunt motor. Therefore, phi 1 is equal to phi 2, here it is in phi 1 is equal to phi 2, that means it will be IA1 upon I2. That means, T1 upon T2 is equal to 30 upon IA2 is equal to x cube, because this is x cube, right. Therefore, 30 upon IA2 is equal to x cube, therefore, IA2 is equal to 30 upon x cube. This is equation 5. This IA2 you substitute here, right. If you substitute, this equation will become x cube minus x square minus 30 upon 23 is equal to 0. So, it is a cubic equation. You will have 3 solutions. So, little bit of trying this, you will get x is equal to 1.55, right. That means, N1 upon N2 is equal to x. So, N1 is 600 rpm and x is 1.55. So, N2 will be 387 rpm. This is the answer for N2, and IA2 will be, we have got IA2 is equal to I1 upon x cube. So, 30 upon 1.55 cube, IA2 will be approximately 8 ampere. This equation little bit trial and error from your intuition you have to try, right. So, such that you will get the reasonable value, I mean approximate value. So, another thing is that speed control of DC motor. So, we know EB is equal to phi z n by 16 to P by A, right. So, n is equal to n, EB is equal to actually V minus your drop in armature circuit. Okay, thank you very much, we will be back again.